Welcome to today's explainer. We're jumping straight to the whiteboard to break down one of the absolute most powerful, elegant tools in all of classical mechanics, the law of conservation of energy. We're going to build this up from first principles, step by step, just like a classic MIT physics lecture, to show you how a seemingly simple concept unlocks the entire universe. But first, let's start with a really fundamental question. Think about it. What actually remains constant when literally everything in the universe is moving? When a body moves through space, its position is obviously changing. Its velocity is changing, its momentum is constantly fluctuating based on whatever forces are acting on it. But as physicists, we are always hunting for that ultimate physical invariant. We want that one magic quantity that stubbornly refuses to change during motion. And that invariant, as we're going to see today, is total energy. Here is our roadmap for this explainer. We'll start by hunting down our invariant, define kinetic and potential energy, look at the law of conservation itself, tackle the messy reality of friction, and finally, scale things all the way up from pendulums to planets. Let's dive in. Part 1. In search of the invariant. To truly appreciate why energy is such a game changer, we have to admit a harsh truth. The math of standard kinematics can be completely overwhelming. Just picture drawing a complex curved trajectory on a chalkboard. Those blue acceleration vectors you'd have to draw are constantly changing, both in their tangential speed and their direction pointing to the center of the curve. Trying to calculate this movement by applying Newton's laws directly means tracking every single spatial coordinate and every vector change every single microsecond. Solving those differential equations of motion directly, it's incredibly tedious. We desperately need an elegant alternative.
That brings us to part 2. Kinetic and potential energy. Let's define the two fundamental ingredients of our universe's mathematical budget.
First up, kinetic energy. We denote this as T or K, depending on what textbook you're using. It equals mass times velocity squared divided by 2. Basically, it's the energy of a body's motion. But here is the absolute crucial detail. Kinetic energy is a scalar quantity. It only depends on mass and the square of the speed's magnitude. That means we get to completely ignore the messy, complicated direction of those bright red velocity vectors in space. It makes the math infinitely cleaner. Next, we have potential energy, denoted as U. This is a system's hidden capacity to do work based entirely on its position within a conservative force field. Think of gravity, where this green energy value, U, equals mass times gravitational acceleration times height, mgh, or a spring, where the energy is the spring constant times the displacement squared over 2. But here is the golden rule you cannot forget. To calculate potential energy, you absolutely have to establish a strict 0 level on your drawing first. For gravity, you have to decide exactly where height equals 0 before you do any math.
Chapter 3. The conservation of mechanical energy. We've reached the theoretical climax of our analysis.
E equals K plus U equals a constant. Imagine writing that in huge, bold letters right in the center of the whiteboard. This is the law of conservation of mechanical energy. In a perfectly closed system, the sum of kinetic and potential energy never ever changes. And here's why that's a superpower. This single equation directly links an object's speed with its physical position. You instantly know how fast an object is moving at a specific height without integrating a single complex equation along a curved path. It's a mathematical shortcut woven into the fabric of the universe itself.
But, okay, there is a vital caveat. We have to divide the board in half here. Conservative forces, like gravity or a spring's elasticity, do work that is path-independent. They only care about your starting line and your finish line. Non-conservative forces, on the other hand, like friction or air resistance, are path-dependent. The longer the messy path you take, the more work they do. Mechanical energy is only perfectly conserved, staying perfectly constant, in a closed system that's strictly acting under conservative forces. Which naturally leads us to Chapter 4, non-conservative forces and friction. Because let's face it, we live in the real world, and real-world systems are rarely perfectly closed. In reality, blocks scrape against surfaces, and pendulums have to push through air resistance. When friction enters the picture, our pristine formula changes. The change in our total mechanical energy is exactly equal to the work done by those non-conservative forces, and that work is negative. Think of it like a leak in a bucket. Friction is literally draining our mechanical energy budget, bleeding it off into heat or sound. The total energy of the universe is still conserved, of course, but our isolated mechanical slice of the pie is shrinking. So how do physicists systematically solve these messy problems? There is a strict four-step algorithm. Step 1, choose extremely clear initial and final states. Step 2, tie a rigid coordinate system to your drawing. And do not forget to set that zero level for your potential energy. Step 3, check if friction or resistance is crashing the party. And step 4, apply the energy equation. If there's no friction, initial energy equals final. If there is friction, initial energy minus the work of friction equals final. Simple as that. Let's look at a classic whiteboard example, a block sliding down an inclined plane. You've got gravity, the normal force pushing up, and a blue friction vector actively fighting the slide. If we just analyze the initial height at the top for our potential energy, the final speed at the bottom for kinetic, and subtract that negative work done by the blue friction vector, we solve it instantly. No chaotic vector kinematics required, just a clean energy budget.
Finally, Chapter 5, From Pendulums to Planets. It's time to pivot away from tabletop physics and look at the grandest scales of the cosmos. The sheer beauty of the law of conservation of mechanical energy is its breathtaking universality. You use the exact same framework to calculate freefall, to find the maximum compression of a heavy spring, to chart the back and forth oscillations of a simple pendulum, and yes, to map out complex orbital mechanics. The identical scalar math governing a swinging pendulum in a classroom is out there governing the stars.
You can see this brilliantly in the gravitational potential formula for planets, phi equals negative g times m divided by r. When physicists calculate orbits, they elegantly set the zero level of potential energy out at infinity. As an object gets closer to a planet, its potential energy drops, becoming more and more negative. So to conserve total energy, its kinetic energy has to violently spike upwards. It accelerates. By just tracking this energy conservation, Kepler's laws and planetary orbits basically fall right out of the math. So I'll leave you with a provocative challenge. Knowing everything we just covered, that total energy must be perfectly conserved, and that gravitational potential energy approaches zero at an infinite distance, how would you calculate the exact escape velocity of a rocket leaving Earth? What precise kinetic energy do you need to blast into that rocket on the launch pad right now so its energy budget is just big enough to reach infinity? Take that magic key, test it against the mechanics of spaceflight, and keep questioning the universe. Thanks for tuning into this explainer, and we'll see you next time.